Hello, my name is Ellen Brayley, and today we'll be talking about the formation of acid halides, anhydrides, esters, and amides. The driving force behind most of the reactions we're going to look at today and see is going to be the stability of the conjugate acid that's formed by the leaving group. And this table helps us visualize this. So we see that the most acidic of all the starting product carbonyls are at the top and the least at the bottom. And basically you can look at this table and know that anything can be used as a starting product to form anything underneath it. And the reason for this is because it's going to have a conjugate acid of the leaving group formed as a product that's more stable than the starting products. So if I want to form an acid halide and I use an acid chloride to start with, then my products are going to be the acid halide and HCl. And HCl is going to be more stable than the starting products that I began with. So we aren't able to use the conjugate acid of the leaving group as a driving force for any reaction to form an acid halide because they have the most stable conjugate acid of their leaving group. But we can use thionyl chloride. So by using thionyl chloride, we have the lone pair of electrons off of this oxygen on the OH group attack the sulfur of the thionyl chloride. This charge, of course, the electrons are going to come in to form the double bond, the chloride's going to leave, and that leaving group chloride is going to come back in an attack at the carbonyl carbon. When this kicks off the negative charge onto the oxygen and that electron pair comes back in to form their double bond, we have this great leaving group. And so when it leaves, we're left with just our acid halide as a product. So now we can look at how to form acid anhydrides, and if we're going to try to use the conjugate acid of the leaving group to drive the mechanism forward, we can look at the table and see that we can do this with acid halides. Also, another way to form acid anhydrides is by using heat to catalyze a reaction between two carboxylic acids. So let's take a look at both of these mechanisms. Very quickly here, this is going to be pretty much the same mechanism you'll see over and over. You got your great nucleophile, got the negative charge on this acetate come in to the carbonyl carbon, kick a negative charge onto oxygen. When the electron pair comes back in to form the double bond, this leaving group that's a great leaving group leaves, and we're left with our product, which in this case is the anhydride. Now this reaction catalyzed by heat, we're going to see the lone pair of electrons come into the carbonyl carbon, kick that negative charge off onto the oxygen. We're going to have this positive charge right here on this particular oxygen, and so in order to get rid of that, we're going to have a proton transfer, which leaves us with our great water leaving group, so that when this electron pair comes back in to form the double bond, the water will leave, and we're left with our anhydride product. Again, using the table method, we can see that in order to form an ester, we can use acid halides and anhydrides. And a unique mechanism using a carboxylic acid can also be used to form an ester called Fischer esterification. Hopefully at this point you're starting to see the common pattern. Here we're going to have the lone pair off of the oxygen, again attack at the carbonyl carbon, again kicking the charge off onto the carbonyl oxygen. When the electrons come back in to form the double bond, it kicks off this great leaving group. This time we do have the positive charge on our OH group, our oxygen, so that chloride that just came off is going to deprotonate that oxygen, leaving the neutral ester and hydrogen chloride as our products. And again, right here, same thing. Going to have this alkoxide, the negative charged oxygen is going to come in and attack at the carbonyl carbon. When the electrons come back in to form the double bond, it's going to kick off this great leaving group, and again, we're left with the ester, and this time a carboxylate product. Now we'll look at the mechanism for the Fischer esterification. The first step is going to be protonation of the carbonyl oxygen. This leaves it with a positive charge. So when the alcohol comes in and attacks at the carbonyl carbon, it's going to kick these electrons over onto the oxygen, neutralizing this charge. There's still going to be a positive charge right here, however, so we're going to do a proton transfer, and that's going to leave us with water, which is a great leaving group. When it leaves, it'll then be used to deprotonate this oxygen, and that will send these electrons to form a double bond with the carbon, leaving us with our ester. So last but not least, let's look at what we can use to form an amide. By looking at our table, we can see that acid halides, acid anhydrides, esters, and carboxylic acids can all be used to form amides. However, with the carboxylic acid, it gets a little tricky because carboxylic acid is, of course, an acid, and the amine can act as a base. And instead of getting the intended product, we end up with this carboxylic salt, and so it's better to use DCC and a carboxylic acid in order to form the amide. So hopefully by this point, the general mechanism here is becoming redundant, but let's look at the second reaction with the anhydride and two equivalents of ethylamine. So you have your ethylamine come in and attack at the carbonyl carbon, kicking the negative charge out onto the oxygen. But even after this electron pair comes back in and the leaving group leaves, we're still left with this positive charge on nitrogen. And in order to deprotonate that nitrogen, we use the second amine. It comes in and deprotonates, leaving us with our neutral amide. Again, here it's a pretty similar mechanism. The only difference is in this intermediate right here, we are going to use this ether group to deprotonate the nitrogen so that that positive charge is neutralized, and this is going to put the positive charge onto that oxygen. But then when the electron pair comes back down to form the double bond, this becomes our leaving group and we're left with our amide product. And finally, as you can see here, we can use a carboxylic acid and DCC in order to form an amide. I'm not going to go through this whole reaction step by step with you because there's another video to detail this in full, but the important thing to remember about this reaction in particular is we get amide as a product strictly because the driving force of this reaction is this byproduct, which is dicyclohexylurea, and it's an extremely stable product that drives this whole mechanism forward.